thank you. I'm a glaciologist, and Daniel Abele, who actually did the implementation of the ice sheet adapter and who also did the simulations, or most of the simulations, can unfortunately not attend the workshop. So I try my very best to talk you through his slides. And if you have any questions then that I can't answer, then please contact Daniel via his email address. There's also a manuscript in the discussion phase now for the Journal of Geoscience Model Development, and the link for it is on the last slide. So I need to admit that this is the only slide where you can see a picture of a glacier. So is this the... Nope. So what you can... This picture was taken during an airborne campaign in Greenland. There's a small Greenland outlet glacier, and here in the center you can see the relict of a subglacial channel. So, and that's what we are most interested in, so how the glaciers interact with the water at the base. So the scale is a little difficult because it's from an airplane, so but the width is about tens of meters. So a very quick introduction in the glaciology that's involved into the talk here. So on the left, there's a very simple setup of an idealized circular ice sheet that we have presented last year on the preCICE workshop, that we have coupled, where we have coupled an ice sheet model to the hydrology. And now this year we went a step further, and now we try to couple to a real ice sheet setup. And I would like to introduce you to one of the many feedbacks that are involved. And the most obvious is about sliding. In ice sheet models, we use a sliding law, we call it, that connects the basal velocity to the basal shear stress or the drag. And this is usually a linear or nonlinear relationship for the velocity. And what's also involved is the K, that's basically a roughness or material parameter. That's kind of a sliding parameter. And then N, that's the effective pressure, and that's basically the difference between the ice overburden pressure and the water pressure. So, and it works, so in a simplified way, it works like, so if the ice at the base is at pressure melting point, you have water that feeds an aquifer. And with more water, you have higher water pressure, so lower effective pressure, so it's easier for the glacier to slide. That we could stop here, that this would be basically the case for the Antarctic ice sheet. But in Greenland, it's different. When we have surface melting happening in spring, end of spring and summer, there's a lot of water available at the surface that drains to the glacier base through moulins and cracks and all those things. And then the aquifer becomes unstable. So it forms channels that can transport a lot of water very quick. And in those channels, the pressure is low. That basically means at the end of the summer, where we have the most amount of water available at the base, the glacier slows down again, although more water is available. So, and we need to incorporate those feedbacks into the ice sheet models to get the seasonality correct. That's not yet implemented in most of the ice sheet models. So this is how our coupling setup looks like. On the left, we have the ice sheet model. We use the ice sheet and sea level system model, for ISSM for short. This is a finite element solver. It basically solves thermocoupled Stokes equation. So ice is modeled as a viscous fluid with very high viscosity. Viscosity is non-Newtonian, temperature and stress dependent. And we also solve for mass transport and all those things, because the ice sheet, they can evolve, so they can advance and retreat. And so all boundaries basically move in time. Yeah, so that's on the left, is the ISSM. On the right is the CUAS, the subglacial hydrology model that we have implemented within the group. It's basically a 2D Darcy flow solver, relatively simple, on finite different grid, and it's only 2D, and it has the ability to switch the aquifer configuration from inefficient to efficient, so evolving the transmissivity of the aquifer. But that's basically the idea behind it. And we couple it with preCICE, and of course, and for that we had to implement 2 adapters basically, one for the ice sheet model and one for the hydrology model. And we had different strategies to do that. So on the ice sheet side, Daniel implemented an adapter that basically allows access to every field within the ice sheet model to the preCICE. And on the other side, on the CUAS side, we decided that because it's a simple small code base, that we put many things of the coupler within the code. And I would like to explain what I mean by that, by simplifying this figure. So when we get grounded ice melting rate from the ice sheet model, so how much ice is melted at the base, we get it as melt in ice equivalent, meters per second ice equivalent. And then we do just a simple scaling to get the water sources, so meters per second water equivalent. So that's very simple. So we could probably do with preCICE. But then we have other things that we need care of. So we get the ice thickness from the model, and then we transfer it to the hydrology, and there we take the ice thickness field together with the bedrock elevation to evaluate via the hydrostatic equilibrium if the grid point is grounded or floated, because the hydrology only works for the grounded part. So with this, we make sure in every time step, in every coupling window, that the domain adjusts to the extent of the ice sheet. We further use the temperature from the ice sheet model. That's an absolute temperature. We convert it to a pressure-corrected temperature to decide if the base is frozen to the ground, because then we don't assume an active hydrology there. So, and with all those informations, we then basically update the mask where CUAS is working on. So, and this happens in every coupling window. I don't know what's going on here. And the only thing that goes back from the hydrology is then the effective pressure. So we solve for the head, the hydraulic head, and this proportional to the water pressure. With the geometry that we got from the ice sheet, we can compute effective pressure, and this is finally the quantity that we need in the ice sheet model. And that's basically telling you the same story, but in the more common way in the preCICE community. So we can discuss this later if you want. When we prepared for the talk, we thought that's basically probably also worth talking about some technical aspects of the work. So how we got actually to the couplet simulations. So there are some discontinuities in the talk. So basically 3 themes. So scaling analysis. Then I will talk about the process of the adapter standardization within the pre-eco environment, and then also I will talk about experiences using preCICE on an actual HPC cluster, because that's sometimes a little tricky. So starting with the first block, that's our setup. That's a medium-sized setup for Greenland. We have 500-meter resolution at the margin of the Greenland ice sheet, where we have the fast-flowing outlet glaciers. And this results in about 10 million degrees of freedom for the Stokes solver. And on CUAS, we have a regular grid, 500 meters, that results in about 12 million grid points. And we simulated 540 days, so 1.5 years, with 30 days coupling windows. And each model did its own time stepping. So CUAS was 4 hours time steps, while ISSM did daily time stepping. And then we repeated all the simulations to get an average about for the scaling. So that's basic. That's then the result of the scaling analysis. And you can see, so on the axis the number of processes, on the left is the time, and the red line is the parallel coupling, and the blue is the serial. And you can clearly see that the serial is always a little faster than the parallel coupling, but the parallel coupling scales a little longer to a higher number of MPI processes. And that's basically because in the serial coupling, no participant has to wait for the other participant. So, because the ISSM is the more expensive partner in this coupling scheme, we had 2 times the MPI processes for ISSM than we had for the CUAS. But we also tried to, here where it's no longer scales very well, we also assigned more processes to ISSM, but it did not help a lot, and it's also very questionable if it's worth putting more CPUs on a process that's no longer scaling well. So if we now look on what the participants do on those scaling analysis, you can clearly see that it's ISSM, so the red curve on top, that's basically not scaling that well compared to the CUAS, but CUAS is anyway the cheaper model. So this is basically an illustration of the individual coupling windows. In the upper row, you can see in the parentheses the total number of MPI processes, and still with the 2-to-1 ratio between ISSM and CUAS. And you can see, first of all, that ISSM has a very hard time in the first coupling window to converge. That's because the initial conditions of both models do not match very well. And you can also see that CUAS finished much faster. So for all the analysis we do, we only consider the last 12 coupling windows. So on the previous figures, it was only the last 12 coupling windows. And what you can also see, if you put in more processes, it's obvious that that CUAS needs to wait for the other participant. So that's not very well balanced. So that is basically the main result of our scaling analysis. And then I would like to go to the pre-eco standardization process. It's a few days ago when the merge request was actually, the pull request was merged actually. And Daniel is, I think, in continuous communication with the preCICE developer team, and I think we are on a good way on getting it done. There are a few requirements that are still a little tricky. So that's basically because of how ISSM works. So ISSM has its executables, but all the models are basically initial conditions, forcing, model setup, mesh, everything is bundled within a big binary. So there's a front end to ISSM that's based on MATLAB, and MATLAB takes care of everything, and then you submit your big binary to the cluster, and then it gets executed. So we will need to find a simpler setup that we can create in Python or something similar, and then we can cross that out. So then this, then R9 is about error handling. It's not yet nice, basically. It's not consistent. And of course, documentation. Documentation always depends on the time and effort people can put into it. So I don't think, yeah, I think it's doable, of course. Yeah, the CUAS adapter is still a prototype, and there are no concrete plans to basically go through the procedure, at least not yet. So this is how the adapter configuration file looks like, and I think the schema for it worked very well for us. So the only thing that we added was basically it's marked here, so options for the solver, so it's ISSM, so that's not part of the schema, and we did so because we can put their command line arguments and something like it into this configuration without having another configuration file for the solver. So that was the main reasoning. At the moment, the adapter can only exchange fields at the base or at the surface of the ice sheet. There is no volume coupling yet, or at least not, also not needed at the moment for us. All the data is exchanged on the nodes, and we make heavily use of the feature where we can just make the translation between the quantities, the field names that are available within the ice sheet model and what's available within the preCICE. So that was a big improvement, and I think that's all to this. Now I want to turn on how to use preCICE on an HPC cluster. So the first option, so it's basically how to run 2 jobs at the same time for preCICE. And the first option, that's the option basically that comes from the preCICE documentation and that you have heard about yesterday. Unfortunately, on our cluster at RV, we do not support MPI run. So there was no chance. And using srun with a node file configuration just didn't work. So Daniel thought maybe you have similar issues, and then he wants to share with you the second option. And this is about heterogeneous jobs or head jobs. And it's very simple. It's all Slurm features. You can just say about the allocations you need for both participants, and then that's it. So that's how we usually run it, and we are very happy with it. There's a third option, and this was actually suggested by Frederick. Yeah. This is about splitting the MPI communicator. And in this example, we use argv0, so the name of the participant, for creating a hash, because it needs to be an integer value. Of course, for our application, this works because they have different names, but if you want to couple the same solver, but with different configurations, you probably want to have to create your hash maybe by the configuration file or whatever. So, and I think, so this, we have very good experience with this, but we have only tested this with OpenMPI. I don't know how it works with other things. Yeah. That's basically about the technical things. And now I finally want to show at least one example on how does it look like. So on the left, that's at the end of the simulation, so at the end of 1.5 years. So on the left, you can see the basal melt rate that we get from the ice sheet model on the extent of the ice sheet. So all white is ice. Gray is ice-free land, and the dark gray is the ocean. And we transfer this to the CUAS model, and then we get the effective pressure. You can't see the colors very well, but you can see we have high effective pressure in the interior, where we basically don't have any melt, and we have low effective pressure at the margins. We have a little too low of pressure at the edges, and that's basically because the aquifer felt dry, and I haven't clipped it for the mapping here for the figure. So, but that's a minor thing. And here on the right, you can see then the subglacial discharge, so the flux in the aquifer, and you can very nicely see how the water gets concentrated into those outlet glacier areas, and how those, I wouldn't call it features, channels, those channel-like features emerge in those regions. So, and then as promised, those are the links for the models and also for the manuscript. And I think I rushed a little bit, so I'm happy to answer your questions.
Thanks a lot for the nice talk. Are there any questions?
Did you try to investigate why the ISSM stopped scaling so suddenly? And it's because it seems a bit sudden, right, in the plot you showed, and not gradual or so.
So we did a scaling analysis also for ISSM alone, and we published about this in 2023, I think. And it's basically because not all of all the modules that are within ISSM are called cores, and the most expensive core is the stress balance solver. But there are other cores that are basically only 2D, like the level set for thickness evolution, level set, and those just haven't enough to do, so they are basically waiting
around.
Yeah.
Okay.
So,
yeah.
And we also had ideas if we could separate those, so having the easy things run on a certain amount of CPUs and the Stokes solver on another set of CPUs, but it hasn't materialized. So.
Okay, thanks.
There's another question.
I have a question about the framework you use to run jobs with the srun commands. Can you explain a little bit more, in the sense, do you have to use some interactive nodes to get these started?
I think I didn't got it.
Basically, my question is, do you need an interactive node to get this srun job started?
No.
Or you can still send some batch scripts within srun?
Yes.
Okay.
And it's fairly easy. So in the third option, you basically just need to create another file, and then within your Slurm script, you can see my mouse. You can provide the file, and that's it. That's a very simple one. But that's the only thing that needs to be in that file. So how you want to assign the numbers of processes.
Okay.
In this case, and this is just everything that needs to be in the Slurm file.
Okay.
Nothing more.
Yeah, more a remark than a question. So it would be nice if we could add this to the preCICE documentation. Right, we have a page on Slurm there, so this could be a very nice addition there. Either maybe Daniel wants to do it, or if not,
Or maybe somebody wants to try with other clusters first.
Could try it here, yeah.
Yeah.
We have the test cluster for this week.
Yeah, so I tried this on SuperMOOC and I couldn't get it to work. That's why it's not in the documentation. Yeah.
This works very well on our cluster. A big problem also is that the cluster administrators are often not aware of a use case like preCICE. So it's very difficult to communicate with them that that we actually need to run both at the same time. So they usually don't have those use cases.
Any further questions?
Maybe a question regarding the simulation results. So at first, your input, is it current data, and do you use the simulation to predict the future?
So not in this so for this setup we use gridded data for the ice sheet geometry to start our models with, and then the geometry evolves within the ice sheet model, and then we transfer every information to the hydrology model. But for this, we don't do any projection runs. So, but this is where I get my money from. So I'm responsible to do those projection runs with ice sheets, but they are lacking coupling to subglacial hydrology. That's why we are working on it. So that's why I'm at the preCICE workshop. So in the last round of ice sheet simulations for the CMIP6 phase, so ISMIP6, the ice sheets for CMIP6, no hydrology coupling was involved. So, and it needs to be very efficient or cheap, so that the ice sheets will pick it up. If it's too expensive, then this will never be part of CMIP. That's why our hydrology is also so simple.
Did I understand it correctly? So in your normal day-to-day simulations, you're using ISSM only?
Yeah.
Okay.
Any further questions? If not, then thank you again